Great. Okay, we are live, and I'm coming into focus here slowly. But welcome to today's live stream. We are discussing the Ruliology of reversible cellular automata, and potentially negative time. Let's see if we get there. So we're joined by Nick, Carlos, and Dugan, and yeah, I think Nick is going to be doing his so he's going to be showing his code today, and we're going to just explore it. So yeah, over to you, Nick, and let's do some Ruliology here.
Yeah, let me just open this. Start with this page from NKS. It's like the thing I was looking in the past few days on this particular page, right? It was talking about how to make any elementary cell automata into reversible one. So first I want to just explain how is it done, right? So it's like I just literally just took some code from here, tweaked it a little bit, and made some and did some Ruliology to find some specific rules with some specific properties that has not just reversible rules but also has some effective motion in time that we want. So first of all, it's like what is this plot is showing? It shows the usual rule plot for CA, just how to turn 3 cells, black or white cells, into another new cell that you can just run. But this one introduces a second order effect. Effectively, you don't look at one step back at the 3 neighboring cells and determine which cell to color next. You also look back one additional step. This is the one additional step on top. So you do something, so you essentially perform the rule. If it's white, you just do the rule, right? I guess the whites here performs the usual rule. So you can see that the bottom row is an exact copy of that rule above for the Cellular Automata 77, right? But what you do in order to reverse it, you essentially add an additional set of rules that does essentially the reverse thing if the which I think it's not correct here still, but just pretend. I think this rule is just maybe showing something. You have to do some different number, I believe. But anyway, pretend that this is just a reverse as exactly on that page. It's a different rule. Like here, it just shows some particular rule, and the top and bottom row is just reverse of each other, flipped. Maybe it's not. Still kind of looks incorrect. Oh yeah, if they're the same, you just flip both of the colors. I think that's what you do.
Okay, that makes
That's
sense
why
now.
that's why I was confused here. Yeah, it's a horizontal flip of each other. Like this is the flip of this one, but when the actual color is the same, you reverse both of them. So that's how you can.
Okay.
Yeah.
Okay. We also have Adam French joining us today. So if you remember Adam, he was doing the project presentation on reversible CAs as well. So we just thought it would be appropriate. And by the way, Nick, are you using a different mic? There seems to be a bit of a reverb or echo there.
Yes, I do. I can switch it. Is it still bad?
Sounds a bit, yeah, it sounds a bit echoey.
It is. Let me just switch to. How about this
Just
one?
for the match.
Okay. All right.
Great.
I don't know why it went. I don't know. That's supposed to be better, but okay. Gonna use the built one. All right. So we did. So what I did is just a simple plot. So now we wanna do some Ruliology of these rules and find a rule. The rule I was looking for is like, for example, this 91 rule is one of my favorite ones. Essentially, I want some property. So this is doing the evolution of the CA from left to right, from some random initial condition. I initialize it with some 90% black cells, 10% white cells. And this is my random initial condition that I evolved this rule, reversible rule. I evolve it like over until this step, and then I reverse it. That's why the picture looks symmetrical. This is just how many times I do, and this is the size of the initial condition, and the boundary conditions are cyclic, right? So that's why it doesn't grow in size. So just fixed fixed height, depending on the size and the time and the size of the initial condition. And the plot here shows the percentage, the proportion of white black cells, I think, right, at each time slice. So, and I was looking for rules that keep this proportion more than random, so not 50-50. Right, that was the original goal. I wanted some proportion, so some favor, so that one of the colors should be favored. If you start from initially from some large population of black cells, I want to be this proportional, at least greater than 50% proportion to be favored, right? And the intuition for that is because we interpret those black and white cells explicitly as some forward and backward types of rule, forward and backward movement in time. So you still have a single computational time because we evolve our cellular automata forward, right, by just applying the rule. But because we made it inversible, and we made it inversible in this explicit way, so that you, for example, you say that black cell is the forward step and white cell 2 steps back is the backward step, right? So we made it explicit. So now you have this dichotomy of rules, one forward and another set is backward. So that if you find some rule that always favors one or the other, you can say that on a global scale in this state, right, the actual observers, you can say, even in that state, who lives embedded in the state, would perceive that it's only the majority of the rules are forward rules. So it evolves in time, even though the computation still at each step goes one by one, right, evolving the state. But because so you get the idea. You have this favoring of some forward rule. So now we have two different ways of talking about time explicitly in this computational sense.
Can we do a quick zoom in on those pixels as they kind of like move left to right? As cellular automata, and based on the resolution that people are seeing it on YouTube, they might not even be able to see the cells here. This just looks like a gray texture. But it's actually really interesting if you zoom in.
It is gray, by the way, because even though we started with black and white, it looks gray because in order to make it reversible, it actually iterates black and white. So it's actually, if you zoom too much, let me make the same plot with just a few steps, maybe, and a small size. I think whatever, ignore this error, right? So maybe that's too small. Let's do it like this, so that you can see the stripes. Yeah, that's a little bit better. So we can resolve that they're actually just black and white colors, but because they're just so close together, when you completely zoom out, they kind of become gray. So it's kind of fun effect. But again,
each one of those pixels is a CA. Each pixel on that image is basically a cellular automata.
I don't think it's like a right way of saying it. Cellular automata is the whole evolution. It's just the rule itself, right? It's like the laws, how to evolve state. So this is just the evolution. This is like a space-time diagram, because it's one-dimensional space evolved in time, so that we can look at it in 2D, right? And this is also just time. But only shows the proportion of black cells, and it always hovers around above 50%. So in a way, black cells always favored, and if the black cell is the forward direction of time, as perceived by an actual observer embedded in that system, right, it would also perceive the forward movement of time. And that's important, even though locally there's some backward effects going on. So in a way, locally there's always some reverse effect. So in a way, some particles start moving backwards in time, forward and backward. But overall, if you aggregate it, it moves forward. Even locally, there's some backward movement persist. Yeah.
Can we do the zoom in at 200? Because today's stream is going to be like quite zoomed out. So just for audience to actually admire these patterns, that'll be really cool. So I have a quick question about this here. So the graph is plotting the proportion of black versus white cells from left to right, basically. but at a certain point in the middle of this plot, it reverses time. It like
Yes.
goes, it starts like going backwards. So is that graph just till that midpoint?
Yes, it is. Yeah,
Okay.
it's only up to this. If I would continue, it would go up back to
Can see
90%
the
started from.
yeah.
Like here, this particular point at the end is actually 90% black. And the way you reverse it is essentially because it's the second order rule, right? It depends on the one step backwards and step. I essentially just compute my 400 steps here, or 4,000 steps, and just reverse two last rows of CA and evolve those, right? And that's how it just reproduces the picture in reverse. But I fire up the same rule exactly, so don't even modify the rule. It's the same rule acting on a different initial condition, which is just the reverse rows of that last evolution. So I
Makes
did some
sense.
Ruliology when I have much more examples. Here, the example when I was running it for all the elementary cellular automata, right? Just small example, so that you can see all the possible patterns that it will do and all the possible populations of black forward and backward time cells. You can call it. Most of them saturate around 50%. So for that particular whatever good target we have, right? It's not very useful because we want some rules like that have some favor in one over another, but most of them are just not. Even though they have some interesting oscillating patterns, we also don't want those because the repetition, when the rule repeats just with some small period, is also not very interesting. So we throw those away. But the 91 one that I will show recently is this one, right? It's kind of that's why it was interesting. I think I turned on those. I think I turned it to bitmap this thing, so because it was too laggy otherwise to scroll through this giant set of plots. So just one image here. I can't zoom in. Another cool rule is this one, 77.1.
That's my favorite.
We just stared. I think this one here. It also has some nice some notion of trajectories even. You can think of, again, if you think of one of those as forward and one of those backwards, you can see that there's essentially some electrons and positrons, you can even call it, right? If you interpret those particles like moving forward and backward in time in some sense.
What is the density settings of this one?
This one?
98. Oh yeah. Can we make it 0.88? This is the one that I was playing with yesterday and I really liked.
8.
Yeah.
Nick, can you expand on why you say you could think of these as particles or trajectories?
Because they look like particles, first of all, but like trajectories. Because again, it's a picture of space-time, right? In a way, just for 1+1 dimensional space-time. That's the simplest model you can make with CA. And
and that would look like a black on a white background moving or something.
there's no, it's like there's no like explicit background.
I know, but in order to interpret it as a particle, you need to have some kind of, right? Because
we don't have to have a background.
No.
There was some intuition
that
if you zoom in at it's maybe make the density much less. There's some intuition that kind of makes sense here. And that's if you look at one of those initial cellular automata states that are moving at exactly 45 degrees, you could think of that as the fastest that a state can be updated in a specific direction, as something like maybe the maximum speed of light. And then as soon as there's an interaction with another one coming at 45 degrees and interacts, there's a slight perturbance in that stream. And the greater the perturbance, the more those strands and those kind of like effects become kind of like horizontal. So from moving 45 to horizontal, and in a way that seems like some sort of, you know, effect of mass or energy or something bending.
Yeah. We can like speculate a lot about those, but keep in mind, it's just a purely computational system, right?
Yeah.
Some physical like effects can be emergent from those, but yeah, it's still a model.
It's just a visual. That's
just
Yeah.
simple models.
I really want to understand though why, because if you say I shouldn't be thinking in terms of there is a background of white and then I see a black pixel moving, because that's why, I mean, that's what you would see in 1D if the diagram looks like a particle in space-time, right? Like I know there's no background. I know that this is just, you know, two binary states, you know, one-dimensional automaton, but if you say it looks like a particle, intuitively you would think of there's like a bunch of white or a bunch of black, and there's like a concentration of the other color that is moving. It's like moving into adjacent positions every step or every few steps, right?
Well, no, if you subscribe to the idea that every particle made out of space-time, like we do in physics project usually, there is like nothing else to make your particles from. You just have vertices in the hypergraph. You just have to tangle them together in some specific configurations in order to call them particles. Here you essentially have the same thing. You have the single substrate, which are black and white cells, and some concentration of those can look like particles, especially when they evolve in time, and you can track the trajectories of those particles. So that's
but I that's what I'm saying. But I am asking that would look exactly like having a bunch of white with some concentrated black, right? Or the other way around.
sure. You just when you have some low concentration of white, you can't maybe call it a particle. It's just a background space-time, right? Because they're also made of space atoms of space. You have to connect the space-time together in order for particle to move through it.
Yeah.
Maybe when it reaches some specific concentration, maybe like here you can call it this pretty concentrated white particle, right? So that's why you can distinguish it from the background.
Yeah, that's the other way to look at it. I mean, another visual clue here is you could think of those little streams of white as maybe a particle, or those gaps of black that are further down as maybe like reducible phenomena that have that persist across time steps. If you go back to the 90, which was the rule that you used previously?
This is the 91. Oh no, this is the 77.
That's 70.
This is
yeah.
Yeah, I mean, my only point was that if you said you could interpret this as a particle, then
or you could see particles in it. Maybe like there's ways that visually there's effects that seem particle-like.
yeah, but I mean, but of course. But what I'm trying to say is, let's go beyond the visuals, right? Like this, let's think about what the thing is really, right?
Yeah, the visuals weren't really the point here. It's just for fun, right? We just
exactly. So,
like my original, as I said, my original goal was just to find a rule with some favoring of one direction of time over another, that perceived direction of time, not the computational time, right? So here we have this explicit. As soon as you have concentration of black or white greater than 50%, this can be interpreted in some physical sense, right? Because now you can link this idea to what in quantum theory you have like ideas of negative probabilities, and like the thing that I tried to explain like last time, that you can simulate quantum computation using some negative backward moving particles so that they can retry some interaction so that you effectively cause some non-local effects and non-local correlations. That's how we can interpret all of those quantum effects, using this backward moving in time and retrying interactions. That's what I was just hunting. I was trying to hunt for in this simple.
Yeah, Richard was saying maybe the word excitation would be a better a better term there. But yeah, back to Nick's point here. It's really the concept of how like different ways of thinking about the progress of time, because And like, how does entropy maybe fit into the picture here? So that I think it would right be to describe it this way, Nick, that as you progress through time, if there's a difference between the concentration of white cells in the beginning versus the end, that's a perceived difference from the observer embedded in that system, that something has changed from left to right. Whereas in the other rules further down, if the balance kind of like stays the same throughout the course of history, you wouldn't really notice a difference between the future and the past. But because the concentration of black cells increase, or there's some kind of like stable difference, that's actually where there's now an observable difference between the future and the past. Is that a different way to describe what you were saying?
Potentially, yeah. Somehow this difference can be discerned from the observer living in the system itself, right? The rule 85. What's about it?
Yeah, so Brady was asking, are the initial conditions 50-50 random? That's a very important point, and we'll elaborate on that just now. The initial conditions are actually very important to get those different types of stabilities.
Yeah. So this is like, yeah, it looks pretty random, some chaotic behavior, but because it's stays the concentrations, essentially reduces the noise, you don't really can distinguish between forward and backward groups.
Can you zoom in a bit? It's like quite faint to see those lines.
There's no lines, it's just mostly triangles.
Oh, those dots on the plot. Oh, the plot itself, I mean, there's
yeah, there's dots
yeah.
there. They just scattered around 50% there. So observer living in this system wouldn't know what direction is forward and what backwards. It's like would look like complete noise.
Yeah, so it would be some kind of, think of it maybe as a minimal observer with only two sensory inputs, black or white cells, like the concentration of black or white cells around it. Like maybe a cell, they can only perceive those two things. So as it's moving around or through time, it doesn't notice any difference whatsoever. It's like maybe floating around in space where there's no discernible changes in any effects around it. You wouldn't perceive time. You wouldn't perceive any difference between moving backwards and forwards. Does that concept make sense, Carlos, like from a time exploration perspective?
What exactly again?
Does that concept make sense? In other words, the idea that to find a difference between moving forwards and backwards in time as the concentration of cells, which is interesting because it's a reversible CA. I think maybe that's the other important point, Nick, is that if it wasn't a reversible CA, then it would be
the point of the reversible CA is to have the point is to have a reversible CA is to actually think of those, because in the quantum theory, it can be interpreted as I trying to explain last time, as actual retrying of interactions, right? If you want to explain some local effects, you want some quantum process has to retry the initial distribution, so it has to send the particle backwards in time, effectively locally, so that it would retry all the interaction and return back effectively as sampled from that distribution again, so that it fill the distribution and perform some inference on it, so that it can output the correlations that it correlated non-locally. Even though it's like your computational time moving forward in time, your effective local interactions can like bounce forward and backwards with this effective black and white cells like things, so that you perceive that it's like globally your time moving forward, but because it bounces locally, you wouldn't be able to distinguish this, but the actual correlation would be achieved non-locally this way, right?
Let's play with a few different initial conditions to explore that concept you showed me previously, Nick, where if you don't get that kind of like Goldilocks initial ratio correct, it doesn't achieve that dominant 60% black.
If you start reducing that like to 80%, to 70%, it already starts to be like there's no clear favoring one over another, kind of bounces around 50%. And if it like start with 50%, maybe not clear. You can see that there's like maybe for the 7-7 it was more clear. Maybe like the trajectories are less clear in that case when you remove that condition. Because there's no like such interactions like here we had, right? Such clear looking like thing like interactions between those trajectories. They're more like random mess.
And what's nice about that one that you just showed is you can see the concentration of black cells kind of like steadily increases almost throughout that entire 1000 steps.
Yeah.
And then if you start with too few, let's say you start with a 99% concentration, how does that look?
Yeah.
There's not
also,
enough interaction. There's not enough kind of like
yeah. Now it becomes
excitations.
boring, even repeatable.
Mm.
So there's some clear phase transition, which is also would be fine to explain somehow between these two behaviors.
So
Very cool.
one question here. I'll have to drop off soon, but before I go, I wanted to ask, what is the reversibility doing here? So I don't have any intuition about this. So how difficult is it to make a cellular automaton reversible? And like, can you say something to that effect? Like,
Well, it's not too difficult. Like this is one method. There are some other methods to make reversible CAs, right? There are different types of CAs you can make reversible, like block cell automaton, or like Adam like last time showed.
Yeah, maybe Adam can comment on that since he's here on the stream.
Mobile
Adam,
cell that are reversible, right? Mobile cell automata. You know that it's not that difficult.
right.
But the point, the intuition here is to study reversible is to draw some intuition to physical case, right? You now want to think of them as physical laws, and they are usually reversible. Reversible means just flipping the direction of time, like putting a minus sign to all your t's in your equations. That's what effectively turns your direction of time backwards.
Yes.
Right.
Right. So I understand the analogy here. Okay, so the analogy here is you have a state, you have dynamics,
Yeah.
the state being configuration of your automaton, the dynamics being the rules, right?
Yep.
And the idea is that apply dynamics forward means the rules that are forward, and apply time backwards, or apply dynamics backwards, so like going back in time, is apply the reverse rules. But I understand that the rules are technically different, right?
Yeah, a little bit. Yeah.
Is there an easy way to show what that reversibility actually means in terms of like how which of these rules activate over time and what makes reversible? Because you said it, the way that this is structured is that it looks 2 rules back, or it looks 2 steps back.
Yeah. Well, we can try running this through automaton. Essentially, what you do to the rule, it's like looks complicated, but essentially you take the rule number. This is just it actually turns to this thing. We just run it for just one step or something. You see that how it acts. So if you act on a 0 and 1 1, with some constant background, okay, for 2 steps.
That's left to right, eh? Or is that up, top, down?
-1. It's a top to right, yes. So let's start with
top to right. Like what? In top to bottom.
Yeah, to top to bottom.
That's a new kind of CA. We haven't related yet.
So this one, which rule it is? You should be able to find it above. Right. So that's essentially one of the
First
top
one?
row rules. This is the 1st
Mhm.
one. Right. So this is the center cell is applying this rule. This is applying this no this one, right? Because now it actually moving backwards. So it's moving this cell forward, but all other cells are moving backwards in this. Well, it depends how you interpret which one of those forward and backwards. But yeah, let's actually
That was
make it
good.
other way around.
Can we try that? Can we try that one more time?
Let's make it out of yes. Yep.
Oh, interesting.
Hold on, why is it so small now? It looks at the cross, yeah. So it looks like it looks here. It looks at this cross, and this is the rule that it actually makes. Right, so we should be able
I
to find
see.
all the crosses. So here and here it should match. Well, that's how we effectively reverse it. If you have arbitrary cellular automaton, it's not going to be reversible, but you want to reverse it, that's how you do it. You just see what actual cell it produces, and you reverse that particular interaction backwards.
Interesting.
And so can you effectively compose the two steps so that
You
we
can-
can see the forward automaton as a single step automaton and the backwards as a single step automaton?
Well, you can clearly highlight it, right? You can already highlight it by the color. But what do you mean compose? You can have different rules, like we had 91.
So I'm just not understanding what that 2 layers of rules means.
Well, this is our
There's
just
there's
this
eight.
is
There's eight.
artificial difference between them, right? Well, this is just a single rule on its own. We just do this difference artificially, so we can call one of them is backwards, another is forward, because we constructively made it so in order to reverse the original one. So it kind of makes sense. But on its own, it's just a rule that looks 2 steps back. So that's why it's a second one. In a way, it like has velocity, right? In order to do some movement, to have some velocity vector, you have to look 2 steps back in order to actually define some notion of direction. So that's why maybe it's also required to be able to reverse direction of movement. Given some velocity vector, you can reverse it. So this is like a purely discrete version of that, as discrete as it can go.
So that row, the bottom 8, what do you call them? Sub rules, are the same as the top. You see where it says rule plot 77. So that's the original CA, and then you construct in the sub rule of 16 rules, where the bottom row is the same as that initial CA, but it's got an extra bit of information at the top.
Yeah.
So then the top row of that reversible CA, those are required. You need to add them to the full set of sub rules in order to make the entire output a reversible CA.
Yeah.
Okay, so then, all right, but let's see if I understand. Is there, forget about reversibility for a second, right?
Okay.
Is there a sense in which you can, so this 2-step automaton can be equivalent to a single step automaton?
And still be reversible. Well, maybe for not for this one, But maybe if you increase number of colors and maybe make it more sophisticated, then maybe.
Mm.
But no, but I'm asking. Yeah. There are trivial examples in which this is true. So that's why I'm asking that. No, I understand. That's why I said forget about reversibility for a second. What I'm saying is, if that stacked set of rules means that you have to look 2 steps back to start the
Mhm.
output, right?
Yeah.
Then it's a natural question, right? Is there a single step automaton that is the same, right? That is equivalent, that produces the same evolution given an arbitrary initial state?
Yeah.
I understand the question, right? It's a natural question.
Well, maybe. Yeah, there's some subtleties because we
No,
already.
but it's a question. I don't know the answer, but you agree that it's a natural question to ask, and it's not clear whether it's true or not, right?
Because it's like this second order acts assumes that you have to have 2 rows as an input, right? It's not very well defined in order to produce the same output as the first order one, right?
Sure,
So
I understand, but okay, but sure, but you can still refine the question by saying,
Yeah.
Given given one row of initial state,
Mhm.
and this set of two order rules, second order rules, right? 2-step rules. Is there so clearly you take the bottom row, so the state, the bottom state, and you evolve with a single step automaton, you get an evolution, right? But to get an evolution out of 2-step automaton, you need 2 rows of state, right?
Is it like
Maybe-
like this?
yeah.
Like can you still achieve reversibility, but you're only dealing with one state? Can you see that?
Yeah.
You mean adding like increasing the radius of the cellular automata?
Increasing the radius, yeah, but it means that you don't need to rely on 2 steps.
It's just when
Oh,
you
it's-
increase the radius, it may be
Mm,
it's gonna break the behavior because now
Yeah. No,
you have
I wouldn't.
more rules applied to the
Yeah,
same.
I wouldn't say so. Let me phrase the question. Tell me if you think this is a meaningful question to ask or not, and then I'll basically shut
Okay.
up because I have no idea about this stuff.
While you're doing the question, can you bring up that example that ran for just 2 steps that I can also visually try to fit in the
Yeah.
idea here,
So
What
the
is-
yeah.
where you had it actually run for a couple of steps, so we could see how
How
the
this one.
yeah, just have that there. Cool.
So the question is, given a 2-step set of rules,
Uh-huh.
is there a 1-step set of rules such that given an initial state of a single row, you can find some appropriate second row of states that might be dependent on your initial row, right? So that
Mhm.
things work out nicely, so that the evolutions are the same for all initial states, right? So basically saying, if you prepare your initial conditions right, you will always get the exact same evolution with the 2-step rules and with the 1-step rules. No. I'm not talking about reversibility at all. That's why I said just forget about that for a
Just
second.
the same behavior, just the same picture essentially. You want to produce the same picture
Yes, same
by
behavior.
first order CA.
Yes.
But you, I just don't get what do you do with the second row, like this 2-step back one, which is
Yeah,
also
I don't think it's possible.
The first,
yeah.
so the first, what you do is so this is the situation, right? You get presented with an initial state. The 1-step rule applies already, and you have a full evolution. For the 2-step rule, you need to provide an additional row on top of it, right?
Yeah.
So what I'm saying is, I'll be happy to say, if you can find, given a two-step rule, can you find a one-step rule that given any one row of initial state, you can find some second row of initial state that you would put on top of the two-step rule to initiate, and then produce the same evolution always, right? In some universal sense. Which it's a sense in which you have existence, right? You don't say it's unique or anything. You just say I can't find some completion of initial state for the two state, so that either the top or the bottom, I don't care, right? One part of it which is totally which is sufficient as an initial state for the one step, right? The other is completed in some way, whatever, in some way. It doesn't have to be unique. But that would, you agree that this would give a well-defined sense of equivalence between these two sets of rule applications, right?
Yeah, in some sense, yeah. It's a kind of equivalent in I don't know, in differential equations, so that you can reduce your second order equation to the first order somehow, right?
But that's exactly the intuition I have in my mind, right? That's why I'm asking it.
Yeah.
Richard actually mentioned here that we tried probabilistic rules with more than 2 blocks. What lookbacks? And the mean field sounds like some physical simulation. I think this is a natural consequence of it being like a PDE solution.
Right. But this is exactly what Nick just mentioned, right? So my intuition is precisely coming from the fact that when you're dealing with differential equations, a second order differential equation can be trivially expressed as a first order differential equation, but you need to make that equivalence complete. You need to like wire things correctly, right? So
well, it can work for some rules, for some it cannot work, right? Maybe.
I mean, what I'm saying is that there are many trivial rules for which this is true, right?
Yeah, obviously.
Because if they do nothing, that's true for all arbitrary order rules. So it's clearly true for some. It is clearly not true for others, right? Because it kind of looks apparent that it won't be true. And then, so that's why I think it's a good question, right? Like you say, well, and by the way, the reason I'm mentioning this, and not to further derail the presentation, but it's just that we have been thinking a lot about this sort of rewriting dynamics or updating dynamics, this discrete time updating dynamics as an analog of continuous dynamics, right? And an analog of time evolution in physics and continuous systems and things like that. And one of the things that we were reflecting on is that it seems we had some behavior that clearly recovered first order time derivatives, like diffusion and things like that. But it was not so obvious how to recover second order time derivatives, right? Which is this kind of like dependence on velocity as a state, which is like an acceleration law, right? And so that's why I was asking, because if you had some theorem that told you something like that, right? Imagine, I mean, this could be true, I don't know, right? But imagine there was a theorem that told you any two-step cellular automaton of this kind, like in the screen, is such that every time you specify an initial state in one row, you can find a second row in the appropriate way so that the evolutions are the same, right? If you were to find that, in my opinion, then you basically just stop looking at two-step automata and you just look at one-step automata, right?
Yeah. Well, hold on, you're doing it in reverse, right? You're trying to reproduce first order cellular automata with the second order by finding that additional row. Or you just find
the other way around. No, the other way around. So you begin with a two-step automaton.
Yeah.
And then the question is whether you can find a one-step automaton that replicates
with the initial condition. You also want to find the initial condition for the first step, one step that mimics this two steps, the evolution of second order with two steps. And
the point is that you have the initial condition is one row that's given. That you have no freedom on that. But so the one step doesn't require anything else.
But you can fix it. But you can find the row, right? You want to find the row that mimics the behavior of two rows and the second order rule.
Correct.
So you're trying to pack all the information into just a single row.
Well,
all of
I
the
wouldn't say
effects.
all the information. I would just say
And the rule.
you only care about one rule. Yes, one rule. Yes, you want to pack your information into one rule.
And the initial condition, which is like one rule. So you also can find that.
Yeah, and then, I don't know. I mean, it's. I'm asking because I have no intuition about these things, but the analogy is very strong, right? Like the analogy, it's
Yeah.
clearly very strong.
We just discretized all space, nothing else.
Yeah. No, I agree, but I mean, this has been in the background of many discussions, right? So anyway, I just wanted to flag it. It's
So
a very important concept, and
would-
we can move on. Yeah.
Would that involve some kind of proof that lower dimension, let's call it CA, is reversible? Or like, how would you prove that you've achieved that, Carlos?
Well, technically, you can't. I mean, if you come up with a proof, then you would need some recursive arguments or something. Like it would. I mean, I would imagine that's super difficult to do, but in concept, right, without the need of presenting a proof for it, the way you would know is by running both in parallel, and you would see that they give the same.
But for how many steps? Like, wouldn't it change after
Well, that's the
while?
thing that like, yeah, that you actually have to run it, like, because of all
Okay.
this like computational reducibility and all that stuff, right? So,
Interesting.
but yeah, but in concept, it's like it would make sense to imagine that, I mean, because there are trivial examples where this is clearly true, where a two-step rule does the same as a one-step rule, right? Because these are, I mean, you could just imagine very trivial rules, like all kind of do nothing or whatever, right? It's clearly true in those. It's probably easy also to imagine some very symmetric ones or something that's just alternating, in which case it's also true, right? But
Okay.
yeah, anyway, that's the
yeah. So I have a question, Nick. Can you explain at that point of when the thing starts going backwards? Is that because the steps ran out, or does that happen by default? So if you run it for 1,000 steps, is the first 500 the point that it reverses as a
Well, it's
consequence
not
of
the
these
reverses
rules? Or?
automatically. I do it by hand, so that the picture is pretty. It's pretty and
Okay.
symmetric.
Symmetrical, I see. Okay.
Yeah. I do it right here. It's like here I run it forward, right? Here I run the same rule, and this is my initial condition. It's just the last two rows of that evolution in reverse. So it's like this is the last, this is the second to last, right? And I evolve it for the same amount of time, and then I just join them together. So.
Okay, so that's basically taking the exact same rule, but with that different initial condition, it starts running backwards, like with the reversed initial
Yes.
condition. Is that what happens? That's pretty interesting. So basically what you're saying is, at any point in time, if you just know what happened one step prior, you have all the rules with which to go backwards in time and recreate every event of the past.
Yeah, it's like reversing the
That's
direction
quite
of
cool.
all velocities of all the particles, right?
Wow.
It's like two roles essentially define the direction, right, where the particles move. If you swap two roles, you effectively reverse the velocity, and you reverse it, and they reverse backwards. So that's the analogy.
It's really cool.
Yeah, that's really cool concept. Guys, it's getting late here. I'm gonna get
Yes,
going.
fellas.
Anyway, yeah, gonna get going.
Cool.
Thanks for the
Cool.
presentation, Nick. Super cool. See you soon.
See you soon.
Let's do good.
Yeah.
So what do you mean by dots? Are you talking about the excitations, or are you talking about the actual like chain of maybe white cells that are progressing? Oh, hold on, sorry, Dugan. Richard says he can't hear you. Just check if your mic's not muted on OBS. I hope they didn't catch that that either. But it's okay. Try again. Okay. Thanks for the.
But my
points out
question
there, too.
is, if someone else can repeat it, is
Mhm.
are there not things that move slower than the speed of influence?
Okay, so Dugan's question is, are there things that move slower than the speed of influence without interactions, without like interference between them? So in other words, if you look at if you take a very sparse distribution initially, and then see if there's anything that moves at a steeper angle than 45 degrees. Is that the question?
So you have this fixed angle of how fast things are influenced and cascade along like a particle moving.
I guess it can't because it's built in, but oh no, but slower. Oh, that's a good question.
Slow, I think it can. It's like if you do the Ruliology like of just like cellular automata, I think some of them go slower. Pretty sure. I think this one already slow. Is it? No. Or maybe it is.
Maybe by construction is not possible. But is that a three-state? Is that a three-state CA? Why is it like gray like that?
It's
think it's the
multicolor,
type.
which would make sense, I guess. I mean, for black and
Yeah.
white, it seems like there's not much you can do. Although
No, because it's
Still
based on
seems to be
construction, right?
variation.
It's kind of like you can only go vertical unless maybe it goes vertical and then for 2 steps. Maybe,
I'm pretty sure we can
yeah.
we can just plot all of them.
You'd have to relate. You'd have to relate on that.
It's like we just plot all of them really quick. Just convince ourselves that
They can hear you now, Dugan. So Brady was asking, did Nick say signals are sent backwards in time? That's not necessarily the right way to think about it. Or
yeah, they're not sending. Yeah, there's a computational time. The only thing that you have to understand that there are two different notions of time explicit here. You have computational time, which is not reversed at any point, and that's the thing that actually makes the space-time, right? That's what its space-time is made of. So there's no causality violation and all that. You just made space-time with forward computational time, but underneath there are two types of rule that one is favored more than another, so that on aggregate you essentially apply one set of rules more frequently, and those are define your forward direction in time as perceived by the actual system.
That's actually interesting.
Here it is.
So, oh, there we go.
Yeah. You can move slower. It's like here you just don't do anything on the left, for example, effectively. You can do it like this.
Yeah, but that's almost like fixed time versus 45, but you can only got like either stand still or go 45 bit. I think also the point to that question is what are you that is moving there? Like who would be the observer that would be progressing at that point? If you're just a single line, then you can only move at the speed of light. It's almost like can an electron ever move slower than the speed of light, or a photon, or whatever it is? Like is it possible for a photon to move slower than the speed of light? Or can it only go at the speed of light? I mean, that's a physics question.
Oh, it's a quantum pi. The point that I was looking into this again is because I was trying to explain quantum effects of non-locality, right? Because those are somewhat naturally to me already can be explained by this retrying of the interactions, right? And in order to retry and explain non-local effects and explain the non-local correlation, you have to effectively send your photon backwards in time, but you're not sending it for computational time. You just locally the loss of movement for that photon now reversed. You just swap the direction of time. It's like swapping the color so that it goes back and reverses everything around it so that it can replay its creation interaction essentially, so that it can be resampled from that distribution. Again, maybe it was part of some creation of entangled particles so that you can create those pairs again and right, so that you can replay this interaction, and somewhat in the quantum process still changed, because you haven't completely reversed the time. So something in that original thing that reversed that photon is still there. It's still inhibiting it in a way, so that, and it keeps inhibiting, and your photon can go backwards, like bounce forward and backwards many times until like until some statistical significance, essentially, so that you can explain all the statistical effects.
That's really cool. It just made me think about, remember when we were talking about which way path information or something like that? It's almost like at one time step, if that's the, go back to the description of rule 77. So if you look at that middle 3-block rule, that's almost like a single time step. But depending on what the time step just on top of that is, there's almost like ambiguity for the next one. So it allows you to make, that's kind of like the quantum state. It's like, it depends on what that almost hidden variable or something is, like the path information of how you got to that 3-block state is like maybe somewhat ambiguous. And then that's what allows you to have this reversible nature.
Yeah, it's essentially like those cells, it's like the actual space-time that's determines the state, the space-time and the configuration space, you can even call it, that determines the direction of movement for the photon, right? And something can flip that, right? Some interaction with some quantum process, maybe it's with some beam splitter or some measurement device, can flip that direction, even though you still computation still move forward, but that flipping also can flips everything around it. It's like acts as a real negative sign. So it's like multiplied by -1. Now you have -1 direction of time of everything, so that everything locally reverses in time, and photon starts going back to its origin, replaying its interaction, so that it can return back to to your measurement device, right? Until something stops inhibiting it, so that you can see the actual statistics, right? Until it like completely removes all the inhibitors in the measurement device, so it can propagate forward, and it's always going to do it because that's the rules that we want. We want the favor of forward rules. That basically guarantees you that it's always going to progress forward, even though there can be indefinite gazillion bouncings between measurement device and its origin, right? Even though they are not perceivable.
And what's interesting with that is once it does go backwards in time, or like negative time has been realized, if you want to use that term,
Yeah,
it goes back to kind of like the initial state, which only has a single line again. It always goes back to the beginning of the universe, but it can't go further back than that. If you were to say that the first line
it
is
may
like
not even go to the beginning of the universe. It only have to go to its origin of creation. It's like, for example, if it, because if you imagine it's especially simple to imagine in terms of physics project and some hypergraph drawing, so that there are some rules also for underlying background of space, right? That always creates some atoms of space around it, and usually and those atoms, because they're new, you don't have essentially there's some action of creation for those rules at some point, and you only have to reverse. You also have to go back effectively when those creations happened for all
to that point
participants in that photon. Yeah, because in the photon
so
there's
how would that state collapse? Like, let's say if that's a quantum state where there's this reversible retrying effect, then how would you describe an observation that kind of collapses that ability,
well, the
or
collapsing
destroys that?
in this probabilistic interpretation, it's not happening, right? It's just the collapsing affecting, or the measurement problem happens why you see only the single photon at your measurement device and not all the bounces, right? It's because there's something inhibiting it. It essentially always reverses the direction of that photon until like some saturation is reached, right? There's some limited amount of time this photon has to go backwards in order to replay the interaction, and when it's like saturates, all the inhibitors went away, then it propagates through your measurement device, and that's when you observe it. But at the point when it happens, all the distribution of those things that inhibits it kind of starts to mimic the actual correlated distribution, something else. That's why it's local. This bouncing back and forwards is essentially what builds up this correlation across multiple locations in space. That's why it makes it non-local. It allows this bouncing back and forward between device and measurement can correlate even different distant locations in space instantaneously, almost as
Is that
perceived by.
is that because the effect of when that thing, to like if it were to go back in time and be resampled from its initial distribution, how it replays to get back to present time, let's say, could put it in a different place, like a different.
Yeah, it can be
Yeah.
turned in a different state. When it's replayed through its creation and interaction and other interaction, it can be in a different state. It can flip the polarization, right? It can put it in a different polarization state.
So instead of in Bob's hands, it could have been in Alice's hands.
Yeah.
It's
like,
and there's some probability that it went either way, and
yeah,
by
we
replaying
had
it a million
this
times.
picture last time, right? It's like
Mm.
there's some probability distribution associated to the origin of the photon, right?
Mm.
So this is the qubit, so we have to convert it into phase space. That's why there are 4 different values your photon essentially can take, right, for the polarization. And then there's some distribution associated to the measurement device. And here they collide. And that's where the photon gets inhibits and gets sent back in time in order to replay this distribution, right? So that's how, and when all the inhibitors went away, that's the photon actually can be played through that device. And that's when we register it in a way,
It's very
macroscope.
cool. So is this, are you developing this these ideas off of some kind of theory or intuition, or do you have a name for this ideas? Like is there references we can draw on here, or is this kind of like a novel approach to thinking about these things?
Well, there's some connections like to quantum Bayesianism because it's related to inference, as we talked about, like statistical inference last time. So you can think of this process of bouncing photon back and forward as it's doing inference. It tries to infer the new distribution somehow, right? So that's why it can be called inference. Also, there's a transactional interpretation of quantum theory when you talk about actual messages sent backwards in time. So they're not very nice from the computational perspective because it's not clear what does it mean to send a message backwards in time. But here at least it's more concrete, right?
What if
So
you send a message forwards in time but just in reverse?
this doesn't help too much. Yeah. When you have these concrete models, computational models, yeah, it becomes more clear. What does it mean to actually send messages backwards?
Yeah. Yeah, it's interesting because there was some research done recently at the University of Toronto about negative time, where a photon wave packet goes through a medium, and the medium somehow reverses the order of in which the wave packets entered the medium. And
It's not really reverses it. It's kind of pushes it forward in time. It's in a way, it's a negative time because it allows to propagate your photons faster through the medium. Well, that's how I understood it, right? So your photons do not being delayed by the medium, so that they excite the atoms, get re-emitted, right? It usually photophores takes time, right? So you delay the propagation, but in some regimes you can actually speed it up so that your photon get ejected from the medium faster.
Interesting. Okay, but it's not you're not transmitting information faster than the speed of light somehow, because it's the packet itself that's still the full informational packet cannot get out the medium faster than the photon.
And I want to understand how it works in this simple discrete pictures. What does it mean to form a packet that is getting, so that you can see more clearly what those backwards and forward directions of what actual photon is doing inside that medium. But you have to discretize space inside this medium in order to make it analogous to that particular experiment. It's not just
guess-
the model, just the internal degrees of freedom, like the polarization. You have to actually make it quantum mechanical, not just quantum computation. That's a bit more difficult.
Could you say that information is something like maybe more than a single state? Like you need a state or like a discrete bit of state, and also just at least one other bit, and it's kind of like a combination of things that you need in order to form information. So information can't travel faster than the speed of light, but maybe there's ways to create patterns that are traveling faster than the speed of light.
Well, no, it's like as soon as you define what speed of light means in a sense of computational time, obviously it's not going to be faster, because it's just your computational time. You're building your causal graph. You have all your causal links explicitly stated as updating events of the state, right? And that's how the speed of light is also defined for the ordering of those events. So there's no way you can violate any speed limits in that sense. Because
So I mean, taking that example with the photons, like if you were to try to recreate that in this discrete model, how would you push something faster? Would that be the equivalent of generating a white cell or black cell at greater than 45 degrees? Like, what would be the equivalent of recreating that?
Well, you can think of this if you think of in these terms. You somehow medium has to inject more black rules, right? It again contains more blackish cells so that you can forward the direction of time that's already in the evolution of that photon, so that you can speed it up, right? It has some natural speed through the medium, right? But medium helps it to move forward faster because it kind of has some additional. I don't know. But there's can be some simple explanation in these terms too.
Is
But I
this
don't
on a
have.
cylinder?
So what?
Is this one on a cylinder? Are there boundary conditions that
Yes,
wrap this up?
those are cyclic boundary conditions. Yeah.
So what's going on at the rear seam on the left and right?
You mean here?
Yeah, all the like in the middle it's gray, but on the edges it's black.
Well, that's the initial condition. That goes from left to right. It's not from top bottom. It goes from left to right here.
You swapped it around to make it more visually.
Yeah, so that it's like time goes from left to right as in this plot.
I see.
See the code there on the second line? It's a transpose. Yeah.
Right, and then it's mirrored on the
yeah,
the second half of the history.
Yeah.
It doesn't need to be mirrored. You just swap the previous state with the current state, and then running the exact same rules, it reverses automatically.
Oh, I see.
So you just it's like saying if at any moment you're like progressing through time, and then you literally just like swap your feet around, and then you end up going backwards in time.
Pure velocity
That
vector.
makes sense. Yeah. So yeah, then it's a true test of the reversibility of the rule.
We can like make analogies to CPT symmetry, but it's like clear that it's like T symmetry is being applied, right? But T symmetry in physics is also known. It's not actually satisfied completely, right? There's some it breaks, like for some weak interactions and all that, right? The actual fundamental symmetry of the universe is the CPT symmetry, when you have to not just to reverse the time direction, but you have to look at it in the mirror and swap the charge. So you turn electron to the positron, right? And also swap its spin, like look at it in the mirror. That's the symmetry that is fundamental. So
you're going backwards towards the future.
Yeah. So that's why those black trajectories, white trajectories are like electron and positron, because if you swap the time symmetry, technically you should also swap everything else. So it's like a mirrored anti version of that. Yeah.
So I see Adam's furiously writing some notes here. Is there any comments from your side, Adam, about this exploration so far?
I found it really interesting. I never heard the speed of light analogy, and yeah, I am like so the flow in time when you start at like 90%, and then when you say that changing the colors to another color is going forward in time, like that graph there.
Yeah.
What happens if you reverse it starting from the initial conditions?
What happens if we start like with 5%? That's what they ask. Or what?
Oh, let's see what 5% looks like.
I think it's gonna be. Well, there's like a.
Oh, that's pretty cool, actually. Wow, I didn't think about doing that.
So like the two regimes simultaneously.
Wait, how did that happen? Oh, wow.
Again, they're jumping around. They iterate. It's like one particular step is dominated by forward moving cells. Next one is dominated by backwards.
Can you
So
just
no way
can you
hybrid
run it
will
for fewer
50-50.
steps so we can like maybe see some of that?
Yeah, we can actually see what's going on. It's like,
Oh, interesting.
it's like looking at white noise. That's very cool. Check that out.
Oh, that's the statistics I can't put there.
Okay, yeah, I see the banding. So the whole like situation flips a lot of the time.
Is that visible on YouTube? Can you try
Slightly.
zooming in a little bit?
Yeah,
No
there was
question
some
being
cases
empty,
there
yeah.
when I ran all of them. I've seen some of those forking, like multiple states. Let's find this.
Yeah, see, here's
They-
why I
like
thought that
here,
85 might be really interesting. Oh, look
here.
at that.
Can you zoom in on those as well? Be cool to look at
No,
some of
I
these
can rerun them. Like, remember
201.
the number.
Okay, yeah, let's look at some
No,
of
those are the
those.
numbers of the rules.
Yeah.
Was that
This
your
is one-
question, Adam? Or
This is one fun.
that's actually interesting as well because it reverses, but then it
But it's still
converges to a
50-50.
dominant.
195 looks interesting.
Which one?
Yeah,
95?
195.
195, 170.
This one?
Yeah, that one.
Yeah.
This is repeats. It's not very interesting. It's actually repeats.
Yeah, it's the same as 170. It's just it has this cycle. It doesn't actually dominate a specific color over time.
Oh, I get it.
So
But
what
it's
we're
spiked
trying to
when
find
repeated.
here is
That's the interesting thing. So some of these have a periodicity too.
yeah, for sure.
Well, they certainly all do. It's just some of them have
Oh,
very
right,
small.
because they're on a finite
because
cylinder. So I mean, well,
Yeah,
that's a
yeah.
question: is the period of the thing commensurate with the radius of the length of the cylinder?
Yeah.
So
yeah.
that's an interesting point there. If you swap the proportions, so instead of at 95, you start at 5% concentration of white versus black. It's just that specific rule that makes it have that effect where it starts doing like some kind of banded bipartite regime or something. But there's many other rules that maybe are more symmetrical. Yeah, that's a good question. Actually, is there a rule that's so symmetrical that if you just swap the percentages from between 95 and 5, it only reverses the colors? Does that question make sense?
Yeah. Yeah, we can also search for those.
Wow, let's zoom in on that. That looks really cool.
Those stripes, that's essentially two regimes running simultaneously. That's fine. They
I
should
wonder if
run
we need to.
longer when it saturates this point. I think it's just because weird.
What's that? What's that problem people get when they see flashing lights too quickly and then they go into like a
Epilepsy.
yeah. Do you think we need to give an epilepsy warning for this episode? I wonder if these things can trigger epilepsy. Okay, Richard had some interesting comments here. So he says he mentioned some names, like he wanted to talk about Fredkin and Toffoli gates. Does that ring
Gates?
any bells, Nick?
Well, those are essentially reversible gates, right? Well, in quantum computation, they're universal. What is it? I always forget. We just put one up. We have a Toffoli gate, which is essentially actually just a CC node.
Okay.
How do you do it? CC. Can I do it like this? Maybe. Something like that. Right, this is like a Toffoli gate. And the Fredkin gate is a controlled swap. It's like this. Those are just like in just usual computation. It's like AND gate, OR gate. It's just some computational thing that you can do. In this case, 3 inputs, 3 outputs. That's why it has to be reversible. So they're reversible. It's just the universality different in the classical and quantum regime. So it's like in the quantum case, Fredkin is not universal, but I think in the classical sense it is reversible. So you can build any classical gate using just Fredkin gates.
Okay.
Out of Fredkin gates, I think. Yeah.
And it's a Toffoli gate, or is
Toffoli
the
gate
full name?
Yeah, Toffoli is not even classically universal, I think. But this is just a quantum version of, or reversible version of AND gate. So we just add, compare two Boolean things. So this is just swapping them, just computing AND.
There was also a mention here of a Novikov self-consistency principle. Have you heard of that?
No.
So I think the description here is in this system, a computer sends a result of a computation backwards through time and relies upon self-consistency principle to force the sent result to be correct. Provided the machine can reliably receive information from the future and provided the algorithm and the underlying mechanism are formally correct. Something to explore, perhaps. It's interesting. You might want to run these kind of rules from an initial cross only and enforce rules which leave the background white.
You mean just starting like with a simple one cell instead of a random condition, some random distribution? You can start with just one, like this, like white or black one. We can,
Yeah.
There's a lot of things you can do.
What is the kind of the
We
scope
see
of
that? Can you run
all
that?
possible reversible CA rules? How many are there? Are there like just if you wanted to enumerate all possible reversible CA rules, how large is that?
Well,
large
like
is that
naturally,
space?
like just the original ones without second order.
I guess it
know
would be the same. Yeah, it would be the same just times 2 because for every single one. No, wait, is that the right way to think about it?
Well, you can definitely reverse any, right? So, right, introducing the second order effect, you can reverse any rule, but you can also see whether the original one was already reversible. But I think the elementary ones, they're boring in that sense. You have to increase number of colors. I think so. Like.
So is it right to ask what the space of all possible combinations of those 16 sub rules are, or like if you just wanted to enumerate what all possible effects are, or is there only like do you have to be? How do you turn that thing to be reversible? Are you just swap in the end result with an opposite color at the top? How do you actually define the making of the reversible set here?
You're asking how I made it reversible or what?
Yeah. So are you?
Well, we can look at this code that actually makes the rule, right? So this is the usual way how you compute, for example, take the digits and compare it to the rule plot for the cellular automata, right?
Yeah.
Those are the digits. The bottom cells are the one cells that
Yeah.
correspond to 0 and 1s here, right? As you can see.
Mhm.
So then you just join them together, right? You just apply this thing. And like that. Let's do it like this. Right? You just join this thing with the reversed. Right? This is the
Yep.
original thing. You just joined it with 1 minus that thing. And you turned it into a new integer. That's how you come up with the rule. And also you specified it with actually a second order so that you can only look at that cell above and not this cells or this cells. You ignore them. That's those zeros over here. And this is like basically defines a mask that you're looking at. That's it. That's how you specify the rule.
So is there one of those for every normal CA that exists?
Yeah.
Is that what you say? Yeah.
Yeah. This is the corresponds to the rule number for one of those elementary CAs from 0 to 255. You do this procedure, turn it into second order, and run it.
255. So does that mean there's 510 reversible C8s that exist? No, wait, what?
No, the same
there's
number.
255. It's 255. Yeah.
56. You should count the 0. So 2. Right.
So
Okay.
what's with the 8 and the 4 and the 2 and the 1? Or are those integers in the sequence?
It's some kind of weights. It's a complicated way to specify how the actual rule acts.
Very cool.
So
I get
it's
it.
not very well
You're counting
documented.
through them up to 16 different combinations of those 3 and then the one above it.
Sorry, what?
I think I get it.
It's just a specification. Sorry, I might have sidetracked Adam's question. Was your initial question answered, Adam?
I mean, not completely. I was just thinking, like, if we're modeling this as you move forward in time, things get more spread out and entropy increases. Is that the way we're thinking about this?
Maybe we can compute the entropy. Actually, we can do it right now. Why not?
Okay, yeah, let's do that. Yeah, this is something I was very curious to see.
So, for example, let's take this rule, right? We just computed it. We just run our cellular automaton again on the random condition, right? Let's set our P to again 98%. And this is our size. Okay, let's 1000 something. All right, so we run it for 100 steps or whatever. So that's the evolution. That's kind of boring one. But what we it's because it's so boring looking thing. Let's also transpose it as we did. That's the evolution, right? Okay. So let's just this is the array. Let's compute the entropy.
What is the formula for entropy? Is there a built-in formula?
Well, essentially, what you have to do is like do the counts of each row. Oops. Right? This is like a probability distribution, and then you just compute the Shannon one. So this is the counts, and I'm gonna just do it explicitly like this. So you do 0, 1. You will normalize it to total. So now it's like a probability distribution, right? And now you compute the Shannon entropy, which is just takes this distribution. Well, we can just count 1 because it's normalized anyway. But anyway, let's do it. We can ignore the second thing. Actually, let's do it like explicitly. Why not? It looks like minus p log p minus q log q. Right? We can do it like this. So that's the number. Oops. And you
add up. How would you plot that?
well, that's how it evolves in time. So it increases. Here you go.
Let's compare that to. Can we add that graph to the
But this is a
next to
direct
the-
function on the enumeration of the ratio.
So that's the distributions.
Right. In this case, like P and Q add to 1, so Q equals 1 minus P.
Yeah.
So this is
just
basically
Shannon
just a
and
different function on the ratio 0 to 1.
I'm just gonna do this. Like, that's the ratio of, depending on which ratio you want to look. Maybe both. Is it going? It's long. No. Well, let's do it like this. This is one of those.
Yeah.
Another one. Just as the entropy. Now there's like concentration of 0. That one is 1. Right?
Can we put this above the actual reversible CA that we ran so we can see what we can try to see how it looks?
We should run it for longer, maybe.
But the entropy, I don't know. I mean, it is true that what you're doing gives a probability distribution, basically the ratio of light to dark along the rows, or in this case, the columns.
Yeah.
But as far as like, can't you give it like a?
So entropy is kind of saturates.
Can you make those bigger? Look at those on top of each other.
So
I guess
my
there's a
what's the 3 different
compressibility
colors?
factor of the bit strings versus, I mean, you could have like a stream of bits, and the way that they're sprinkling, that they're being peppered into the bit stream, is being lost in this way of measuring. I don't know
Hold
if
on,
that's
Sorry,
what
are you
is
asking?
something that's.
so can I just ask a question about what's being plotted here? So is that the concentration of ones and zeros or blacks and whites, and then the blue line is the entropy, total entropy, as you progress through time.
It's almost like complete noise. It's like one maximum entropy, 1 bit. Is it 1 bit? Is it reach? Does it reach 1 bit? What's the maximum? Well, not quite. It's close.
Let's run that initial state at the 5%, the 5% version. Is this still rule 90? No.
5%.
Oh, or just whatever the that alternating interesting thing was we had before.
It's kind of because the
Oh, they're
alternate.
swapping it.
Yeah, they swap.
Wow, so it's a mixture between what color is that? Some weird color. I'm sorry, Dugan, back to your question. What was your question again? Can you zoom in on that so we can see those bands?
Yeah, I mean, I guess like an alternative question would be, how compressible is each row in the computation?
How compressible?
Yeah, how complicated is it?
Well, it's pretty complicated because it's almost maximum entropy, so it looks like complete noise.
Well, if you had like, okay, if you had half of them being white, half of them being black, if they were checkered, was white, black, then that would be highly compressible information versus if they're randomly spread out. Like, how are they actually spread out in space or in memory, and what's the compressibility of that bit string?
Is that the same as what this entropy is here? Can you Nick, is this possible? It might be difficult, but can you extract what the final row in the first row looks like, and then compare that
And
to
from
this
the
plot of the entropy?
and from the array itself.
Yeah.
Like first and second.
Yeah. No, first and last. Yeah.
Yeah, the last. Oh.
That's the lot. Is that the lot? Oh, okay. Yeah. I mean, that looks.
Yeah.
That looks
The
pretty
first one
random.
was almost completely zero, right?
Mm.
And the second one almost 50-50. Well, not really, but 60. Alternating between, is it either 40 or either 60? Looks like more.
So the question here is, even if it tends towards being a more black regime, does the entropy still approach 1? Or by default, because it is majority one color, does that necessarily
That's
reduce
zero.
the entropy?
Yeah, if it was just completely black, it would be zero entropy.
Yeah, but what I'm saying is, like, in that rule where it's the 60% black.
But
Or is
if
that
it's
what's happening here?
50-50, if it's 50-50, then it's maximum entropy, right?
Mhm.
Here it's like 60-40. So it's almost, I don't
This
know
is
why.
60-40, right? Yeah.
It's like what we just computed is essentially like if you do compute it for this distribution, you get this one, right? For pure one, it's the way we define it, but it should be zero.
Okay.
Right. Because it computes logarithm from zero. And for 50-50, it's 1.
Yeah.
So it's
Okay.
pretty close to 1. It's not
So it's interesting that it gets close to 1 even at 60-40. You would have thought that would be quite far from near maximal entropy, but it's not. It's the log.
Yeah, it's because it's logarithmic or whatever.
So
The point is
here's
that
a
it's not
question.
much.
Were there any rules that you found that takes it more majority one color versus the other that's greater than 60%? Like, were there any rules that ended up being like
so.
80% one color versus the other?
No, not like 80. Well, it depends on the initial concentration too, right? So,
Yeah,
but the one,
that's true.
but the one I run here, I think like this number here after the arrow is the like average of the last 1,000, right?
Okay.
That's how it can look. Like this is boring. Like this is essentially 36. It's pretty
36,
nice.
74. So we're looking for a number far away from 0.5.
Yeah, I'm looking for stable behavior, not like jumping around, repetitions, and also farther away from the middle.
So that's kind of an interesting point there, is that most of these things, it's hard to get away from increasing entropy. Like, it seems like entropy always wants to take you to maximal entropy. It's hard to get away from it completely. more than, let's say, 90% or not,
Yeah,
whatever
69.
that metric
69.
is.
Yeah.
That's 70-30. Okay, so let's try that one, 70-30. That's further than 60-40, right?
Which one? 7?
So if we run the rule 130,
This one.
yeah, then what does that entropy get us to?
It's kind of the graph kind of looks very uniform, but let's look at it. The rules are tried. It's very high definition. Oh, let's sorry. Resolution. Renders. Yeah, I know what's happening there.
There's
Looks
something
boring.
happening there. There's some kind of weird strands coming in there.
Yeah.
Unless that's a what do you call it? A visual artifact based on
That may be.
pixelation or something. Wow. Well, when you zoom in, it's kind of interesting.
This white line is very weird.
It's a particle. We found particles, guys. What is that? Is that a white hole?
Is it because it was like high concentration of white
Super interesting.
at this
So
particular?
what's the entropy of this graph? Oh, there's more.
Yeah, it's because it started with some high concentration of white, so somehow stable.
Persists.
Start out at 50%.
All over the place, yeah. Then so if we go back to that one where it was 70% concentration, what does the entropy get to by the end of that that run?
You want the same rule? You
Yeah.
compute with what? How much? 70?
The one that's how was it set up initially?
It was 98. Actually, can I go? Let's do more.
So it gets to about. Oh, look how it's. This is a cool rule. Look at that. It's so crazy how these phase shifts happen. You just adjust one little number and then it completely changes the pattern. This is nuts.
It's interesting how there are 3 different values
That's so cool.
coordinating between.
Yeah, I guess it's black, white, and then checkered or something as like a third.
Because you started like this is very low concentration, essentially like only 2 white cells here, right? And they were propagating here and split because the boundary conditions split it in 3 regions. All that. Yeah.
Yeah, so that kind of there's a line there that's less than 45. If you look at that, like
Right. It's like some collision
yeah.
between 2 different forces, and the collision is happening slower than speed of influence.
And then at a certain point after collision, there's some retention of the pattern. Then it just seems to become chaotic after that. But the interesting part, so if we run that entropy measure on this plot, is that chaos? Is that like mixed regime at the end? Is it how far away? How entropic is it? Because what's interesting there is even though it looks like it's totally mixed up, it's actually 70% black cells.
Which rule was that?
No, the last one that you had there. So rule 130, 999. What was the concentration? 999.
Oh, the rule number. What was the rule number?
130.
Oh, okay. Okay. It was 99.
I think it was 999.
let's I want to see this one. It's actually lower entropy.
So 0.9, yeah, that's what I'm saying. Yeah, which is kind of interesting. Like, and if you look at how it looks like it should just be chaos.
But low entropy because it's like the concentration is less. So essentially like was around 69.
Yeah. So really, entropy is just really a measure here of the mixedness of the average mixedness of the states. Like if you were to make a prediction, if you just make a bet, like over the next 1,000 steps, majority are going to be black or majority are going to be white, how often would you win? And the lower the entropy, the more your bet would be flexible.
What do you call it? It's like always, yeah. Depending on the initial concentration or what. And
I don't know. I was trying to see if I could rephrase this to build an intuition of what's going on here with the entropy.
Well, entropy is just like in this case, we just something simple. We just feed it the distribution. It essentially shows you how far away it's from complete noise, or how close it is, rather. Well, right? Nothing else. We don't use any other properties of entropy, so that it's like additive and somehow convex and things like that. Just any notion of how close it is to noise would be fine. The fact that we're computing some more algorithms doesn't matter.
Very interesting. Okay, so back to Adam's question. Did that answer your question? Finally?
Yeah, I mean, I was mainly looking at the graph at the beginning, and I was thinking that if we choose one color to represent the flow of time,
Yes. Yeah.
then, I mean, like for this one, for example, based on that initial condition, if we reversed it from the initial condition, what the graph above would look like, that line plot.
It'll just be
It's like the same initial condition,
Yeah.
just colors flipped. That's what you mean.
Like reversing it from the first two rows of this CA.
Oh. Let's try it.
Because I was wondering if it like the graph is just continues and asymptotically goes upwards from the other side.
Yeah, so let's do.
No, Brady made a good point there.
This
It could
is
just
forward,
be that
right? What is... Work. And the backwards, just fix. This is the initial condition. So instead of this, we use the reversal we need. Right. So the forward one looks. Again, transpose it. Run it for longer. And then just join it so that we can look at it back to back. Just what is it like? Reversed? Yeah. But it's like to the right it goes forward, to the left it goes backward. So that's.
And can we look at that, the line, the plot of the distribution of the colors?
That's cool.
Well, we can kind of guess. Here we can do it too. So for this joint thing, where's the distribution thing? Just do it for this joint. This is Let's do this. That's expected.
Yeah, that answered my question. It's like the framework I have right now is that like there's the start of the universe, and then everything kind of like spreads out a bit and gets a bit more jumbled, like entropy increases. But I'm confused because there's the idea that entropy increases, but also you can't reverse entropy. So that's just what's going on in my mind. I don't know if it means anything.
We can reverse it because we assume infinite states, right? So there's always some Poincare recurrence things that you always back to the same state because there is just finite amount of them.
Oh, I see. Okay.
Wait, can you elaborate? What do you mean by finite amount of what?
Because you have a finite state, right? We have a size of how many our init is like.
Yes.
So this is the size. So that's the amount of possible states that there is, right? If it's like a giant number, but you can still enumerate all of them theoretically. So after you go through all of the steps, you always, at least this many steps, you always come back. That's your higher.
That answers my question. Do we know if these will always approach the same like limit? As in this one, it seems to be going to 0.4 on both sides.
I think maybe not necessarily. I'll look. Have to do outreach.
Why would it be different? Why does the intuition think will be different on different sides?
Who knows?
I was just wondering, but
we can search.
Yeah,
we can search for those rules that have this different behavior. It's another point.
I guess
Maybe
because of that. Yeah, it's because of the rules. Actually, so Brady was making the point here is that does that concentration of black versus white always end up being the same as what the concentration of the original 16 sub rules are black versus white?
No, it always reduces, right? We started from 98. We're starting with very high concentration, and then it goes like to 60, 69, right? So it's kind of reduces. So it's never. I was looking for that tries to maintain the same distribution. So at least in the elementary case, CAs, there is no such case. Maybe if we increase the number of colors, maybe there's such rules. But if you start with 98% concentration, it stays the same. And still have some nice behavior, some not trivial behavior.
Yeah.
So.
Can we save that exact image right there? I think that'll make an awesome wallpaper. Pretty cool. All right, that was really fun. A lot of comments in the chat here. Actually, just the one here was somebody brought up digital mechanics. That when you Google it, some information comes up from Edward Fredkin. So we'll share this paper here. It's kind of interesting.
I think Fredkin actually who come up with the second order cellular automatons.
Oh,
that's his idea. Yeah,
interesting. Cool. And then last comment here in the chat, Roger Penrose, conformal cyclic cosmology theory addresses the problem of entropy in the universe by redefining black holes as cosmic sinks that resize entropy. So there you go. A little side quest for people to explore after the stream is finished and you still feel like you haven't mediated enough. Okay, cool. I think that's it from our side. Dugan, Adam, any last questions?
No, but that was great. I really enjoyed that. Thank you.
Good stuff, Nick.
Yeah, a lot of fun.
Yeah, good stuff.
Great. Okay, so until next time, just remember there's NKS Book Club every Sunday, so you're welcome to join us on the Discord for that. Wolf from Winter School will be happening first thing next year. So I think we're kicking off on the 6th of January, I believe, to be confirmed. But just visit our website, wolframinstitute.org, to subscribe and join that as soon as the forms open up to join the winter school. And we're going to be doing a lot of this kind of stuff for winter school next year, a lot of physics. So yeah, please join us for that. Cool. Okay, until then, thanks everyone.